Good morning, everyone. Can you hear me?
Yes, good morning. And we can see the solving impulse and momentum problem screen.
Okay, great. If you send me an email, I'll respond to them after the class, okay? I saw the mail, but I've not been able to respond. And someone asked when the midterm 2 will be. It's on the 17th, but I'll post it as an announcement on Moodle as well. Okay. So next week is our reading week, right?
Yep.
Okay, great. Okay. We've been looking at momentum, and in our last class, we discussed momentum and we started with impulse. And then we talked about impulsive forces. We took some examples. But today we want to look at solving impulse and momentum problem. We also established in our last class the impulse momentum theory. We'll look at that briefly today as well as we progress to discussing conservation of momentum and the laws that define the principle for the conservation of momentum. Okay, so we'll begin today with solving impulse and momentum problems. Now we are used to seeing tactics or approach or strategies to solving problems. And we discussed a lot in the last class when we treated previous classes, when we treated the free body diagram and also how we applied Newton law to solving problems. And we have been applying Newton laws to solving most of the problems we've been looking at. But for impulse and momentum problem, Newton's second law does not apply appropriately to solving such problems. But we'll have Newton's law that applies better than the second law. That is the Newton third law. And that is because the Newton, in terms of momentum and impulse, that is discussing collision of objects, it is actually the law that talks about action and reaction that will be most appropriate to describing this, okay? And this tactics we want to look at is following the same trend like what we've seen in the free body diagram and all that, which we'll be taking some ideas from those ones to establishing this. Okay, but it's just that we'll be describing them using the language of impulse and momentum. So we'll basically be talking about Newton's third law, but we'll be speaking the language of impulse and momentum to describing the action-reaction pair of forces. Okay, so in solving impulse and momentum problems, we'll have 5 basic steps that we should keep in mind. Now, the first, whenever you're given a question, you will make a sketch of the situation as usual. We've been seeing that. We'll try to visualize what the issue is, what the question is demanding from us. Now, to do that in terms of impulse and momentum, we use the before and after diagram to understand exactly what is happening. We saw that in our last class, the very last exercise we did, the before and after situation, to help us define initial and final momentum, initial and final velocity states. Okay, so we define before or immediately before the interaction and immediately after the interaction. Those are the area of focus. Then we move on to establish a coordinate system. And how do we do that? When we describe the before and after, we'll be able to say, okay, is this thing moving in the S plane or Y plane? We define the direction. Is the direction positive or negative? Because sometimes the question will not specify. And sometimes you have to make assumption. And if you want to make assumption, you have to specify that, okay, I assume this to be on this plane. You specify your assumption such that the person looking at your script will be able to follow your thoughts, to mark the script. And the next will be to define the symbol. And what do we mean defining the symbols? We simply mean bringing out the mass and the velocity for the before and after interaction. And also, in defining the velocity, you should be able to tell if it's going to the positive or negative direction. All right. Yeah, position is not an emphasis. We have seen time also in the definition of impulse, but they are practically not an emphasis when it comes to defining your symbols because they are going to be dependent on the velocity of the object. All right. So the next will be to list the information provided from the questions. What they tell you is happening before and what data is happening after. You'll be able to also bring out the information that are insinuated if they are not given expressly in values. Okay. So the final will be to identify the unknown. What exactly is the question asking you to do? What is it asking you to look for? What is the question saying you should solve or find? So let's quickly see an example of how we apply this strategy to solving a problem. So the very first that we'll be looking at today, hold on, please. Sorry. The first one we'll be looking at today is the example of the baseball. All right. So we have a 150-gram baseball is thrown with a speed of 20 meters per second. And then they give us the mass of the baseball. It hits straight backward. It is hit straight backward, the pitcher at a speed of 40 meters per second. The impulsive force of the bat on the ball has the shape as shown in this figure. That is figure 9.10. The question now is, what is the maximum force? One, that the bat exerts on the ball. What is the average that the average force that the bat exerts on the ball as well. So we said the first step will be what? To draw the before and the after picture, visualize what is happening. So we'll have the before picture here. The ball was thrown at the speed. Now, in the question, it was not exactly specified that the ball was thrown in the positive or S direction. So we are going to be assuming now that the ball was thrown in the negative S direction, okay? And it was hit back towards the positive S direction. So having established that assumption, we'll bring out the before picture. The ball was thrown at a velocity of 20. Now I've specified the direction, which brought about the minus 20 meter per second squared per second that you see there. Then the mass of the ball is given to us as 150. Taking that to kilogram, we'll have 0.15 kg. All right. So establish our coordinates. We see that the ball is moving in the negative X at the initial, then after the hit or interaction, the ball changes direction towards the positive, okay? And it moved at the speed 40 meters per second. So our 40 meters per second remained positive. So our initial velocity is minus 20 and our final is 40, all right? So we have given the symbol. Then we list the information. That is what we have done, bringing out the mass, initial velocity, and final velocity. These are the information given in the question. And then we identified the unknown, which is find the F max and F average. Okay, so from the picture or the graph given to us, we can see the time interval, that is the change in T, for this impulsive force interaction. It lasted for 0.6 milliseconds. And we see the peak as the F max. And we remember in our last class when we talked about average force, that is your impulse being equals to force average and change in T, okay? But if you look at this question, this equation, we will have two unknown, all right? So it means we're going to use another understanding of definition of impulse to get our values. The first question is we're looking for the F max, that is the maximum force here. So we take this relationship. Remember where this one came from the impulse momentum theorem. We said that change in momentum is equal to the impulse, and impulse is also equal to the area under the curve. So the area under the curve will help us with the information we are looking for. So now we're going to use the information about the area under the curve to get our F max. Okay. So from the information provided, we can actually get the change in momentum. So we'll have the final velocity, which is 40, initial velocity, which is minus 20. If we input that into this equation of change in momentum, we'll have the mass times the final velocity minus, remember the value of the initial velocity is negative, minus will make it plus. And that's how we got 9.0 kilogram meter per second. This is what happened in the very last exercise that we got. That is why the answer was F, because the initial velocity was actually negative. So by the time we substituted into the equation, it gave us 2 minus and brought in the plus. Okay. So having known this value for change in momentum, now let's apply the equation that says J, which is impulse, is equal to the area under the curve. The curve is a triangle. So the area of a triangle is half base times height. Okay, so we'll have half this value, the height, then the base. So half the F max we are looking for, then the base, which is 60 milliseconds. When we convert that to seconds, we'll get 6.0 times 10 raised to the power minus 4 seconds. So we can make F the subject of formula. That is, I'm jumping, but let me not jump, let me follow the exact step, okay? So 2 went into this to give you this value, all right? So we have F mass times 3.0 times 10 raised to the power minus 4, okay? So our value for, we have already calculated our change in momentum. So impute that into the equation, change the momentum equal to area under the curve, which is 9 equal to product of F mass and time. Make F mass the subject of formula, which is the maximum force. We'll now have 9 divided by 3.0 times 10 raised to the power minus 4 to give us 30,000 Newton. So we now know our F max. So from the definition of impulse that we know before, we can look for our F average. Okay, so just make F average the subject of formula. That's how we got this. We know the value for our Jx, which is equal to change in momentum from the impulse momentum theory. So have this value of Js to be 9.0 divided by the change in time as we see in the diagram to get 15,000 Newton. So we see the F max being 30,000 and the average being half of that. So mostly, like we saw in the last class, our average usually gives us about half the maximum force of that system. Okay. Okay, so let's talk about another interesting thing about momentum that we really did not emphasize in our last class. It is called the impulse approximation. We know from our definition of impulse that impulse is actually the large force exerted at a short period of time. And we saw some examples. The common one is like the baseball we just saw. But there's this thing about that interaction. Whenever such large force happens, we also have other forces that we could analyze. But we noticed that they were silent, we ignored them. Why? Because they are actually small, like the friction force that will exist between the ball and the bat at that short time. Because that force is small, we tend to ignore them. It does not just happen only in the case of bats and ball. Whenever we have impulsive force, we tend to focus on the impulsive force only. So when we do this and ignore these small forces during a brief impulsive interaction, impulsive force contact, we say we are approximating the impulse. So this process is actually called the impulse approximation. That is we tend to ignore the small forces, other small forces that could be part of that interaction. So whenever there is or we use impulse approximation, the initial and final momentum and the initial and final velocity values immediately before and immediately after tend to be the same. Okay. And it is this information that helps us establish the laws of momentum. All right. So we just keep this approximation in mind. We have been doing it, but we did not recognize it as impulse approximation because we have not discussed it. Okay. So whenever we just focus on the large forces, this is exactly what we are doing. Impulse approximation. All right. So we'll take an example, then we'll move to the conservation law of momentum. So we have researchers, scientists who research on several birds and their motion, how they go airbound, how they fly from rest position. Okay, so we have some scientists saying that some have to initiate the first motion by putting force from springing off from their leg, and some will have to do that from the wings. So in one experiment, a 190-gram crate took off essentially straight upward from a force plate that measures the normal force on the ground on the quail. The net upward force of the quail is as shown in this figure, that's this one. Then the quail left the ground with this velocity at 3.5 meters per second. Now we have 3 questions to attend to from this description. A, approximate the impulse by estimating the area under the force versus time curve. B, what is the change in momentum of the quail as it leaves the ground? C, give the value you found as the quail execute a rapid takeoff. Does it use mostly the leg or mostly the wing? Now, when we get to that C, I'll just make a short comment about quail habitation and how they actually influence our own discussion on that C. So the first question is that we should estimate using that impulse approximation the area under the curve. And like I said, we've been using it, but we did not just recognize it as impulse approximation. So we notice that this figure is like the very first example of the figure we saw before we brought in an approximation of the shape like the rectangle. But in this case, with the kind of shape we have, the approximation that will apply or the definite shape that we can bring in is a triangle. Okay, so we began our approximation by ignoring some slight forces. This is what we mean by ignoring the small forces that gives us the definite shape. Okay, so when we ask a question with definite shape, it means we have actually done the approximation to give you a definite shape. So from this shape, we cannot really have a particular formula about this parallelogram. So we introduce the triangle. We'll see in the triangle we introduce, we see the SS areas and also the triangle exceeding the given point. It's an approximation. We see that this area protruded beyond the curve to make up for the SS's. Okay, so we're going to use this information to answer our question, to calculate the area under the curve. So we know that we're going to use the area of a triangle. We see the value here, the end are shifted backward so that we reduce our value. This one went forward, that should increase former value. Okay, so let's proceed to visualizing. Because this was provided, this was the first step we took. Then we visualize the motion of the quail. Initial velocity was 0, so we see that it's taking the motion on the y-axis. Everything about the s-axis is 0. So we see the mass as given to us in gram. When we took it to kg, it gave us 0.190 kilogram. We're asked to find the change in momentum as well. So we'll move on to attending to the first question using the image from the triangle approximation of A that we saw here. So the figure A is what we're using. Our momentum is actually the area under the curve, which is half base times height for the area of a triangle. So the value here, half, will have our base, which is the difference between these 2 points, okay? So this is actually 1.25. This one went beyond backward less than 0.05. So we'll have 0.045 times, this is about, we'll trace this or trace it here because this is where we're using. We'll have 13 is above half because it protruded beyond this. So this is 13. So that's how we got the 13 that we're using to get our momentum in the y direction to be 0. The momentum is going in the positive y, okay? 0.05, 0.52 kilogram meter per second. Now the second question asked us to look for the change in momentum. Change in momentum is actually the difference between the initial and the final. For the initial, it's going to be 0 because mv is 0, so that takes care of that. And so our change in momentum is actually equal to the final momentum, which is the mass of the quill times the velocity as given to us in the question to get 0.67 kilogram meter seconds. Now the last question said the bird from our calculation, the values we obtain, use the leg or the wings to fly. Now, quail is the kind of bird that spends most of its time on foot. So majorly, the activity of a quail is majorly on its foot. And whenever it's going to launch into airbound, it uses its foot. Research stated that. So our finding already agrees to that because 80% of the value of the change in momentum is provided from the impulse from the leg. So from our value, we can categorically state that the impulse from the leg is actually a small amount of the lift. There's a small amount of the lift provided by the wind. So majorly, it's coming from the activities from the leg. Okay, so let's proceed to the conservation of momentum, which was our emphasis in our last lab class. Okay, so if we visualize, remember we said in understanding this, we're going to be speaking the language of impulse and momentum. And in our last class, we used the examples of cats. We have several examples that we can use to picture this, but let's look at the collision of two balls. So we have system where two balls collide. We see in the first case, they are moving in opposite direction, coming together. And then immediately after the impulsive force interaction, they moved their separate ways. They had the action-reaction pair, which tells us we can actually use the Newton's third law to typify what is happening in this case. So they moved in different directions. And remember the rules of the Newton's third law. They are going to be moving in opposite direction with equal magnitude, right? But because their direction is opposite, one is going to be positive and one is going to be negative. So using the understanding of Newton's third law to describe our impulse for these two balls before, during, and after. So we see that the impulse for ball 1, on the x plane, that's what we mean by J1x, on the s plane is equal to the negative of the magnitude or impulse of ball 2 in the s plane, according to Newton's third law. Also describing this from our understanding of the impulse momentum theorem, which is the impulse being equal to change in momentum. We see also that for the change in momentum for the ball 1 will be equal to the impulse for the ball 2, and that also applies to the second ball. Okay, so what does this imply? That is the influence on the total momentum, which we have stated in our last class, that total momentum of that system is the summation of the individual momentum of the system. So we'll have the total momentum, capital P, being the sum of P1x, P2x for the two balls. And now, after the collision, we can see that that final momentum is equal to the initial momentum. Why? Because it did not change. The collision did not change the total momentum of that entire system. So based on that, because it did not change, we now have that the total momentum on the S plane is conserved. It remained constant. And it is this idea that gave us the what we call the Newton, the conservation of momentum of a system. Now, taking this idea to understanding the laws that applies to determining if a system has a conserved momentum or not, we're going to, because when we now have a complex system with more than just two pair of action-reaction, what do we do? How do we determine the conservation of momentum process in such a system? In our lab class, we limited ourselves to the first state where we can expressly state that the momentum of a system is conserved based on the kind of collision we saw. We saw in our last class the inelastic and elastic, which we'll be looking at in our next class. Okay, so if we have a system that has more than one action-reaction pair, how do we understand the conservation of momentum? So we introduce first the system ideology. Okay, now picture the system ideology like, example, a tree. A tree has several parts interacting. Okay. So if you have any comment or want me to go back to any slide, you can just raise your hand, then I'll bring it to the mic, because sometimes I may not be clicking on the chat to see what you want to tell me, okay? So the tree has the branches, the leaves, the roots, all of them functioning together to form what we call the tree. So we'll call all that a system. But we'll have also the tree interacting with the sun, the environment, during photosynthesis process. Down the roots, we have the interactions with the other micro activities, microorganisms, the process of absorption of nutrients from the soil. So let's picture that as a system and also use the understanding of the interaction of that tree with the other parameters that are not within the tree as the environment. So we'll now have a division of system and environment. So we're going to use that ideology to understanding the laws of conservation of momentum. So we see a system here. We use, like we did in the free body diagram, the circle to represent the boundary of that system. All right, so we'll have the system of 1, 2, 3 balls. They are all going to be interacting with each other based on action-reaction pairs. So for such a system, we will now establish some rules that will guide our understanding. Okay, so we see that as long as we can describe the interaction of such a system with the action-reaction pair, we will notice that there will be no change in the total momentum of that system. And if that happens, when the total momentum of the system remains constant, we say that system momentum is conserved. Okay, so we also use this idea to generalize to every other system if they're going to exceed more than 3, like we're seeing now. As long as the total momentum of the system is conserved or remains unchanged, we'll say the momentum is conserved. And the thing is that the point we should note is that in the system, we have internal forces. The description of the conserved momentum is describing majorly the internal forces, which is the force that are in the action-reaction pair. Okay, so we now have the system having internal forces interacting with each other. What now happens when there's an external force? Let's say someone brings in something now to hit one of these balls. That has the potential to change the total momentum of that system. So that will now give us another kind of system where we have external forces acting on this object. And we already know that these external forces can actually change the momentum of that system. So when then do we say such a system is conserved or not? It is actually this kind of complex system that brought about the laws that we want to really quickly emphasize. We have seen some of the laws, that is stating the internal forces of a system remaining the same. We have seen also that whenever they collide, they move kind of from the Newton's third law with the same magnitude in the opposite direction, so we say it is conserved. So when we now have a third case, third scenario, where external forces are actually influencing that system, are we going to be able to point out the state where the momentum is conserved from when it's not? When there are external forces, we have emphasized that it will change the momentum of that system. So we cannot state theoretically that the momentum is conserved, but the momentum is going to obey this principle. Okay, you know this came from your J average and all that. So the momentum from the impulse momentum theorem for a system that has external force will be, the change in momentum will be the external force acting on, let's say, the particular ball 1 times the time interval for that action. So we'll have the total momentum of the system as usual, like the summation of vectors, which means for the P1, external force and change in momentum for change in time for that, for ball 2 and ball 3. So if we bring out all the forces, we can see this is constant. We bring out our T multiplied by the various force. So we now have that this expression is actually a net force. So we can summarize it here that for a system that we can identify external forces acting on, the change in momentum, okay, we use this arrow to define it as vector, is the net force, product of the net force and the time for that interaction. Now, when we say net force, we're not referring to the internal forces, which we saw in the previous case, the internal forces that are majorly action-reaction pairs. No, we're referring to the external forces. So the net force refers to external forces. So for us to be able to state that such a system can actually have its momentum to be conserved, the net force has to be equal to 0. And by that, it means we will have a system when the net forces has no more influence on that system. So there's no net force. The total momentum of that system will then remain unchanged when there is no net force that will bring about that change. So for a system that has no net force, we said such a system is an isolated system. So this should give you an idea of the definition of isolated system, because we have several kinds of systems. All right. So the isolated system with net force equal to 0 will always have its momentum to be conserved. Okay. So that gives us the summary of what we mean by the Newton, sorry, I'm always using Newton, the law of conservation of momentum, that the total momentum of an isolated system is constant. So when we use the word isolated system, you know what we mean. A system where the net force is, external force is 0, no external force. So the interaction within the system do not change the total momentum. Thus, the final momentum is going to be equal to the initial momentum. When this happens, we say there's conservation of momentum. So the law of conservation of momentum is majorly emphasizing an isolated system. Okay, that is a system that has no external force changing the momentum of that entire system. So by implication, we are saying the total momentum after an interaction is equal to the total momentum before an interaction. So the interaction in the S component, the total momentum after is equal to the total momentum before, either in the Y or S plane. All right, so let's take an example to buttress that point. So the example of Bill, the way to Bill is going to jump on a sled, so like he's playing, and the best way to do that, to initiate a kind of speed to enjoy the snow ride, is to make like a kind of run, then you jump on that sled to initiate a motion. So Billy did this and started running at 4 meters per second and launched her body weight on the sled weight. And then the question is, how fast is the sled moving after she landed on it? So first we picture, this is the system before, after, and before. She ran, this is her body weight, 26 kg as given in the question. She was running at 4 meters per second speed, which is her initial speed, but the sled is not moving, so the initial velocity of the sled is 0, and the mass of the sled was given to us. So I've identified the before condition, atomizing our parameters, right? So when she jumped on the sled, she proceeded with one velocity, so both her velocity and that of the sled moved as one. Okay, so we have the final velocity, and the final velocity is also of Billy is also equal to that of the sled, okay, which will just give us the final velocity of the system. And the question is saying how fast, which is what is the final velocity. So for both systems, with the parameters given and the question asked, we can actually use our understanding of conservation of momentum laws to solve the problem. Okay, so we'll start solving the problem. The final momentum is going to be equal to the initial momentum. Where did this statement come from? From the conservation law. And momentum, as we know it, is mv. So we can see the mass of B and the mass of the sled, mv, for the final outcome, which is the P final, to be equal to the P initial from this statement. Okay, so the mass of B and the velocity of B is the initial, because for the slid it's going to be 0. V 0 multiplied by the mass is going to be 0. So from this statement, we proceed to getting our initial that will help us obtain the final value. So we'll have, which is what I just stated, how we got this to be the only remaining expression. This is 0, so it takes care of this, so this remains. So our final, when the two masses are moving at the same velocity. So if we make, in this case, V as the subject of the formula, we know the value, this is our initial, this is our final. That's what we are doing here. So we'll have something like this. So don't be confused. V Bx initial being equal to this. MB plus MS final. So make this the subject of formula with this. That's how we got this one. So this is the equation. We assume viewing this, that's equating this to this. That is P final to P initial. That's how we got this expression here. So substitute the values that are given to us, 26 plus 5 times the initial velocity to obtain the final velocity to be 3.3 meters per second squared. Squared is velocity. Okay, so I encourage us to also see the example 9.6 of the test. All right. So we'll move quickly to the final discussion of the day, which is explosion. We also saw this part in experiment, that is the very last part of the experiment. Explosion is usually, it comes from expansion of the spring or sudden expansion of gases to bring about an interaction or impulsive force that can either be within an isolated system or outside of an isolated system, okay? But our emphasis or focus is for an isolated system, all right? And by that, we simply mean a system where the external force is, or the external net force is 0. So we see an example we saw in the lab for the sudden expansion of spring that brought about the kind of reaction we got for those two cats. So let's see an explosion where the particle of the system moves apart briefly after an intense interaction. And what happens mostly, they kind of move in the opposite direction when they collide, okay? And if the system is an isolated system, it simply means the total momentum during the explosion is going to be conserved, all right? It's going to remain constant. Why? Because the system is actually going to have only internal force interaction, which is the action-reaction pair of interaction. So let's take an example. A 30-gram ball is fired from a 1.2 kg spring-loaded toy rifle with a speed of 15 meters per second. The question is, what is the recoil speed of that rifle? So we picture the problem and identify it as an isolated system. That's why we'll have the circle around it to show it's isolated. So we bring out the symbols, then the parameters given. From the question, they gave us the mass of the ball to be 30 grams. So we took that to kilogram. And then they gave us the mass of the rifle, 1.2 kg given to us in kg. The velocity of the ball is 0 at the initial. The velocity of the mass is 0 at the initial. Okay, but after it was fired, there was a recoil on the rifle, and the ball also moved at the velocity that was given to us in the question. And the question is now saying, what is the rifle's recoil speed, which is the final speed for the rifle. So we'll also proceed to solving the problem using our understanding of conservation of momentum, which is P, because it's in S plane, final being equal to P initial. This is the conservation law. So we'll have the P final being the mass of the ball times the velocity of the ball plus, it's going to be the total sum of the momentum of that system. That of the rifle and the velocity of the rifle, and this is what we are looking for, which is unknown, is going to be equal to the initial. So if we have something like P initial and P final being equal, if we bring P plus this, it's going to give us 0. That's the extended part of the equation. So this is our P final being equal to P initial, and our P initial is equal to 0. 0, 0 velocity. So there's no momentum in the first state because it is stationary. So we now have that this P, this expression is equal to 0. So it means M B V dx for final is going to be equal to, move this to this side. When you do that, there'll be a minus because that's cross the sign of equality. MR V R final. Okay, so if you make this the subject of formula, this will come under this, all right? So that this will go off here. That's how we'll have MR here. So we'll have MB, MR times this V final for the ball, okay? Now this negative sign is emphasizing direction, all right? Which you can see from the picture here. The rifle moved in the negative X direction. So that's why this negative is following us. Otherwise, the magnitude of this system is actually 3.8 meters per second. So we substituted directly with the information provided to get the final answer. All right. Okay, thank you so much. If you have any comment about all we have discussed today, if there's any point that is not clear, feel free to send me an email or a chat. Ask your questions anytime. And for the week, we're not going to be having lab on Wednesday and Friday. Now, reason being that we'll be doing a revision for our midterm 2, which will be coming up on the 17th, the Wednesday after the reading week. Okay, so, and you are asked to drop off before the close of today the lab reports on the pigeonhole at the lab, entrance of the lab. You see the post hole there. Put it in that hole, and at the close of today, we'll go there to pick it up. So you try and do that before the close of today. Also, you can drop your assignments there. We'll have them sorted out. All right. So let's quickly, I encourage you to read the examples of the 9.8 as stated here. Somebody was asking if what should they read for the test 2, midterm 2. Midterm 2 is going to cover the second part of the class that is starting from where we stopped the first time to where we'll be stopping by Friday, which will be the first part of chapter 10 by Friday. All right. And then the revision is not going to be in person. It's going to be online because For Wednesday, I can be available in person, but for Friday, I'm not. So I figured the best way to be even for everyone is to make it online for everybody. Okay. Yep. Somebody's asking, can you post this new slide on Moodle? Now, the new slide is on Moodle. What I'm doing is I'm updating the file every week. So I expect that if you downloaded the class the first time, download the class again today, it has been updated. By Friday, it will be updated. Yes, Kate, you can come on the mic.
I just wanted to clarify. So
It's not updated.
Okay.
Yeah.
So this coming Wednesday, we don't have in-person lab. It's just on, or we have in-person lab, or is it online? Which one's this Wednesday?
This Wednesday, there will be no lab. We'll be doing a revision class online.
Okay, thank you.
You're welcome. Okay, let me try and see. Yeah, the slide is on Moodle. Download the updated file. The file now is updated, okay? That's November 8th, Monday. Okay. Yeah, November 8th, Monday. Yes, you're correct. November 8th, Monday, because for Friday, the Friday lab has been done. It's not November 8th, Monday. That will be your reading week. Okay, I'll confirm that and post it as announcement on Moodle. November 8th, Monday. For Friday lab. Because of the Friday group. Okay. Okay. So I have
I have a question. It's not updated on Moodle as yet. It's the same from Friday.
the file will have a Moodle.
Yeah, it's not updated.
Okay, I'll see to that. Okay.
Okay, thank you.
You're
And
welcome.
for Wednesday lab, our lab report and assignment is due Wednesday, correct?
Your lab report and assignment is due Wednesday on the 5th. Okay, so yeah, that is what sorry if I have to pronounce the name this way, okay? Zacharias was correcting us about that. By Monday will mean Monday the 8th, the first day of the reading week, not Monday today for the lab. All right. So you can drop off that Monday the 8th. Okay, not today, like I announced earlier. So
Okay, thank you.
you're welcome. Okay, I'll update the file as soon as I end this class, but I think I did before the class. All right.
Dr. Charity, I
Yes.
have a question about the lab. So in the steps, it says that we're using a 250 gram weight for on top of one of the carts. But then on page 4, it says a 150 gram weight. So do you know which one's the correct weight?
Which weight did you use in the lab? Did you take note of the weight you used?
No, I didn't. I just thought it was the 250 until I read the last page.
Most of us did use the 250, and I'm not sure until I check the instruction manual now to be sure it's not just a question you have to answer with 150. Is it just a question? If it's a question, then you have to use the 150. Like if they change the weight on the cart, what impact would that be? I'll check, and that's
I don't think that's the case because it just says remember to include the mass of 150 on the cart. Okay. So I think it's just reminding us that we had an extra mass on the one cart.
Yeah, the extra
we use
mass,
a 250 gram weight, not the 150.
Oh, okay.
So you use the 250. I saw your mail, but I've not been able to reply, but I will after the class.
I didn't include that question in the email. I saw it after, so I just thought I'd ask you right now.
Okay. So if the question is, if it's not a question on its own, specifying what the effect would be if the mass happened to change. Then you should use the mass that we used for the experiment, which is 250.
Okay, sounds good.
Okay,
Thank you.
you're welcome. Okay, is that all for me today? All right, have a great day. Bye-bye.
All right, thanks. Bye.
Have a great day.
Hi, I have a question. So,
Okay,
when is the term test 2? I mean, midterm 2,
17th.
17. Okay.
All right.
And it'll cover until the end of,
Yeah, I think we started the second from chapter 5, right? To
Yeah.
the early part of chapter 10.
Okay.
Okay.
All right. Thank you.
Thank you. Have a great day.
You too.